This video is for Chemistry in the Earth System, Unit 1.3, the cycling of matter and energy. Today's essential question is, how do energy and matter interact as they cycle through Earth's systems? Our first main idea, thermal and solar energy. Matter is any substance that takes up space and has mass. Most matter on Earth exists in one of three states: solid, liquid, or gas. Remember, a fourth phase of matter, plasma, consists of highly energized charged particles. The addition or removal of energy is needed to transform matter from one state to another. Important compounds and elements that cycle through Earth's systems include water, carbon, nitrogen, and phosphorus. While they cycle, they sometimes undergo a change of state or a change of chemical identity. Thermal energy is internal energy responsible for the temperature of an object. Nuclear energy is generated during nuclear reactions. Fission describes energy released when an unstable atom splits into smaller particles, and ionizing radiation, which includes alpha, beta, gamma, and neutron radiation. This radioactive decay transforms an unstable atom to a more stable configuration. Fission occurs in Earth's interior. The heat it generates is called geothermal energy. Fusion is the process in which atoms combine to form larger atoms, and this process occurs in the sun. The sun is primarily hydrogen. Inside the sun, 4 hydrogen atoms fuse to produce 1 helium atom, which contains 2 protons and 2 neutrons. The helium atom's mass is smaller than the 4 hydrogen atoms that combined. The loss in mass is converted into solar energy, the light and heat that power the sun. We can harness this energy to power our devices and our bodies. Thermal energy movement. We've already discussed that thermal energy travels in 3 ways. Radiation describes energy, as we've already discussed, that travels in the form of electromagnetic waves. Solar radiation enters Earth's atmosphere in the form of short-length, which is high energy, electromagnetic waves on the daylight side of the planet. On the dark nighttime side, much of this energy is radiated back into space in the form of long-wave or low-energy radiation. This process removes large amounts of heat from the atmosphere, and if Earth did not expel much of this solar energy back into space, the planet would overheat. Conduction is the transfer of heat from molecule to molecule or atom to atom through direct contact. One particle collides with another, transferring some of its energy as heat to the other particle. Conduction is a transfer of energy you experience when you touch a hot object. When hot magma comes into contact with other rocks, its thermal energy is transferred to the point of contact by conduction. Lastly, convection is the transfer of heat through primarily vertical movements in fluids. Convection occurs most commonly in gas and liquid substances because heat moves with the fluid, establishing convection cells. Convection cells also have horizontal components as rising particles spread out, cool, and sink back down to produce a cycling motion. This is illustrated by placing a pot of water on the stove. As the water heats up, it becomes less dense and rises within the pot. As that water cools, it sinks back to the bottom of the pot, completing the cycle. Convection also can happen in fluid-like solids, such as the material in Earth's upper mantle, which is called the asthenosphere. Uneven distribution of heat. Although its incoming and outgoing solar radiation is balanced, Earth does not heat evenly because the planet tilts at 23.5 degrees. At any given time, one region of the planet is exposed more directly to the sun's rays. When Earth's southern hemisphere tilts towards the sun, it is exposed to solar radiation for a longer period. And the sunlight is more concentrated on the southern hemisphere and dispersed over a wider area in the northern hemisphere. This corresponds to summer in the southern hemisphere and winter in the northern hemisphere. When the northern hemisphere tilts towards the sun, it is exposed to solar radiation for a longer period and receives more direct sunlight, and at the same time, sunlight in the southern hemisphere is dispersed over a wider area. This corresponds to summer in the northern hemisphere and winter in the southern hemisphere. These changes are magnified in the northern hemisphere because more land is situated in the northern hemisphere, and land absorbs and loses heat more quickly than water does. Earth's uneven warming affects air near the planet's surface. Radiation heats the surface of Earth. Heat imparts energy to air through conduction or direct contact with the warmed surface. Warm air rises, leaving behind a region of lower air pressure. Cold air sinks, adding cold air to the lower levels and increasing the air pressure. This cycle of rising and sinking air forms convection cells, moving warm air away from the equator and cold air away from the poles. Global bands of air pressure form at the equator, which is low pressure, 30 degrees, which is high pressure, and 60 degrees, which is low pressure, and then 90 degrees, which is high pressure at the north and southern latitude. Winds form between the pressure gradient set up by the global bands of air pressure. Remember, a pressure gradient is the extent to which pressure changes over a given distance. Air moves from high to the low pressure bands. The wind distributes heat and moisture around the planet. Winds also move water across oceans' surfaces, producing surface currents that distribute heat, moisture, and nutrients around the planet. More importantly, surface currents carry warm, saline water to higher latitudes. This water freezes at the poles, increasing the density of the water beneath. This produces density currents that sink into the deep ocean. Thermocline circulation describes the flow of density currents throughout the global ocean. This circulation mixes ocean waters and helps regulate Earth's climate. In summary, convection, conduction, and radiation transfer heat through Earth's systems, affecting weather patterns, climate, ocean circulation, and tectonic plate movement. The water cycle. Earth contains many systems that interact with each other and that cycle matter and energy. Scientists have analyzed each of these systems in detail, determining the boundaries of each system, the initial conditions of each system in Earth's history, and the inputs and outputs of each system. Diagrams and models help describe the functions of the system. The uneven distribution of heat on Earth drives several crucial cycles of matter and energy. The water cycle describes how fresh water moves between the land, ocean, and the atmosphere, passing through the three states of matter at or close to the planet's surface. Each transition or phase change requires the addition or removal of energy. With the addition of energy, ice melts to form liquid water, and liquid water evaporates to form water vapor. With the removal of energy, water vapor condenses to form liquid water, and liquid water freezes to form ice. When a great deal of energy is added, ice sublimates directly to water vapor. When a great deal of energy is removed, water vapor deposits directly as ice. As water evaporates from the planet's surface, the gaseous water vapor in the atmosphere produces humidity. And when water vapor condenses, it forms clouds. When the concentration of water droplets or ice crystals in clouds is high enough, the water falls from the atmosphere back to the planet's surface as precipitation, primarily rain, snow, or hail. The precipitation recharges oceans, rivers, and lakes. It also percolates through the rocks and soil, recharging aquifers. Greenhouse gases in the atmosphere, including carbon dioxide, trap heat from the sun that would otherwise escape back into space, warming the Earth. This warming of the atmosphere by the heat absorbed by greenhouse gases is known as the greenhouse effect. The increased temperature has an impact on the water cycle. Evaporation rates will increase, which in turn increase moisture in the troposphere, or the lower atmosphere, leading to more precipitation. Because temperatures are higher, this precipitation is more likely to occur as rain or snow. Changes in global climate patterns caused by global warming also impact precipitation patterns. For example, models predict that as climate change continues, precipitation will increase slightly in most of the United States, but that summers, particularly in the South, will become hotter and have longer periods without rain. The same model predicts minor increases in precipitation in the northwest and northeast of the country. The rock cycle. The rock cycle describes how rocks change over time. Like all cycles, the rock cycle does not have a true beginning or a true end. Igneous rocks are formed as magma cools beneath Earth's surface, and lava cools at or on Earth's surface. Rocks on Earth's surface are broken down by chemical and physical weathering, producing sediments. These sediments are deposited and compressed to form sedimentary rocks. When sedimentary or igneous rocks are subjected to changes in temperature or pressure conditions, metamorphic rock forms. If the temperature increases sufficiently, the rock will melt and form magma that gradually cools to form more igneous rock. At this point, you should be able to generate a full and complete response to today's essential question: how do energy and matter interact as they cycle through Earth's systems?